So this is the example of nozzle. So actually it is reflect the same ideas of free jet, but to be specific we call it as a nozzle in this chapter, because the shape of the nozzle is actually influence the flow rate. So we can safely use the centerline velocity at point 2 as a reasonable average velocity as shown in figure 2a. If the exit is not smooth, well-contoured nozzle, but rather a flat plate as shown in figure 2b, the diameter of the jet dj will be less than the diameter of the hole dh. This phenomenon is called a vena contracta effect. So in this slide is actually I would like to introduce you one effect called vena contracta effect. So it's a result of an inability of the fluid to turn the sharp 90-degree corner indicated by the dotted line in the figure. So here the idea is, so about the pressure, so the pressure for the moving fluid in this point after it passed through the nozzle, so the pressure here is equal to P atm. So mean you could assume that it is equal to 0. However, the fluid flow or the diameter here will affect your calculation of flow rate. Okay, as we learned previously, we have a continuity equation, we have mass flow rate, and we also have volume flow rate. So for volume flow rate, Q is equal AV. So and then in this situation, so Q is A1 V1 is equal to A2 V2. So here what you need to be careful is, let's say we have a hole like this one. So the wall is very sharp like this one. So as said here, water, the fluid do not have ability to turn 90 degrees. So means that the molecule here, so it cannot turn itself 90 degree to move like this one. Okay, so molecule needs to flow in curve, in certain curve, to get out from this one. So means that the cross-sectional area that comes out from the nozzle is smaller compared to the cross-sectional area of the hole. So means that when you calculate A2 V2, you need to be very careful. You cannot take the cross-sectional area of the hole. You need to measure what is the cross-sectional area of fluid that comes out from that nozzle. So this is the very important, because if not, you are calculating wrong continuity or wrong flow rate in your problems. So we call this one, we call the reduction of the cross-sectional area here as vena contracta effect. So to calculate this one, to create an equation for vena contracta effect, so we need this definition. So we need to know what is the diameter of the jet. Means jet here means the diameter of water jet, or the diameter of water that comes out from the nozzle. So and then we need to know the diameter of the hole. So the diameter of the hole is the diameter at the hole here. So you could measure it if you do the experimental work. You could measure the hole. So and then the design of the nozzle is actually will give us different value of vena contracta. So for example, if the wall is sharp like this, so it will have the CC here is equal 0.61. So if we have a little bit curved nozzle here, so the CC will become 1.0. So it's quite good, because the cross-sectional area of water here is 100% same with the diameter of the hole. So and then if we do like this, okay, so and then we have a CC of 0.61, not much change from the above design. And if we have calculation design like this one, so the CC is around 0.50, mean it is worse compared to the previous or the first design here. So the best one is this one. So what is CC? So CC is this one. The vena contracta effect is a function of the geometry of the outlet. It can be obtained by experimental and called as contraction coefficient. So CC here is a contraction coefficient. So to calculate this one, so this is the equation. We just get the ratio between the cross-sectional area of the jet. So AJ here is the area of the jet. So mean the area of the fluid that move out from the nozzle. So this is the water jet. So in some textbook we call it as jet. So and then we divide with the cross-sectional area of the hole. So the hole here is the hole that you have in your wall. So means that the ratio of this one is contraction coefficient. So we simplify it as CC here. So and then if you calculate the CC here, please make sure that the maximum value for CC here must be 1. It is because if the water jet cross-sectional area is 100% same with the hole, so mean your vena contracta coefficient, contraction coefficient here will equal to 1. So later on we will see example of the calculation that using the CC here.